All right, the Wittig reaction. Let's suppose that we needed this alkene. How would we make it? Well, we know we can make alkenes by dehydration. We just did that. So how would we think about dehydrating it if we thought backwards? We would probably draw something like this and put the OH, or the water, add the water with the proton on the least substituted carbon, and the hydroxy group would go on the most substituted carbon. Now that would be a reasonable retrosynthetic plan, but now let's think about this in the forward direction. If we treat this with H2SO4, which would be our E1 elimination reaction, we make the carbocation, but we see that there are two alpha hydrogens. This one I'll call 1. If we lose H1, we would produce the desired alkene, but if we lose H2, we would produce a different alkene. So we could lose H1, that would produce the desired alkene, but if we lose H2, so that's the H1 pathway, if we go the H2 pathway, oop, no carbonyl there, just a CH2. We produce this endocyclic instead of exocyclic double bond. This is a tri-substituted 1, 2, 3 double bond versus a di-substituted double bond. So which would you predict is more thermodynamically favored? So then we would follow someone's rule. Do you remember the name of that rule? Look it up if you don't remember. So we would predict, and in fact, according to our textbook, we get 9 parts to 1 part. Now, if we needed kilotons of this to have the drug that's going to cure everyone or prevent everyone from getting COVID, for instance, that wouldn't be good because we'd be wasting most of our material. So how can we put this carbon-carbon double bond here in the thermodynamically disfavored position intentionally and on purpose? This is such a powerful technique that George Wittig received the Nobel Prize in Chemistry for this. He received it at the same time as H.C. Brown for hydroboration. One of my graduate mentors, Gerhard Kloss, was in Wittig's group and actually turned down the opportunity to do research on the Wittig reaction. His wife, future wife at the time, I think she was not his wife, a female graduate student in the group, finished the work. And that was part of her dissertation, the discovery of the Wittig reaction. So, what is the Wittig reaction? The Wittig reaction is the reaction of a carbonyl compound. This can be an aldehyde or a ketone with a Wittig reagent. And for our class, these are going to be triphenylphosphenes with a double bond between the phosphorus and the carbon. Now, I'm going to immediately actually draw another form of this. So I've drawn this with a carbon-phosphorus double bond, but the way this is going to be, to conceptualize it, it's going to be best for us in terms of understanding the reactivity, is where we push those 2 electrons over. That puts minus on carbon, and then the phosphorus would be plus. So this is the ylide, and there are lots of ylide. There's zwitterions that in one of the resonance forms we can put an anion and a cation on adjacent atoms. And this reacts and puts the double bond in exactly the place where the carbon-oxygen double bond was. Now the other product here is triphenylphosphine oxide, and that phosphorus-oxygen double bond, we've seen it before, for instance, in phosphoric acid. That's one of the strongest bonds out there in nature, and this phosphorus-oxygen bond strength is one of the thermodynamic driving forces for this transfer of the carbon to the carbonyl compound and the loss of oxygen. All right, so let's look now at our problem that we had. We want a high yield of this specific alkene. So for our specific example here, let's take the carbonyl compound that we would need, which would be this ketone. Now, let me illustrate for you the Wittig disconnect. If we're thinking backwards about this, we're going to take that apart, and we would have this carbonyl. Now there's the other one, formaldehyde, but formaldehyde's not a great choice here. Cyclohexanone, widely available, readily available, and inexpensively available. We would now want to react that with the Wittig reagent that we need, and we just want the one where there are two hydrogens here. And if we do that, we make the alkene exclusively at the desired position. So it's only here at the desired position. Now, the question is, how do we get at the Wittig reagent? And it turns out those are pretty easy. The Wittig reagent. We take triphenylphosphine. It's an air-stable aromatic phosphine. Phosphorus is right under nitrogen, so it's a little bit like ammonia or an amine. And we can react it with any number of alkyl halides. We do need a hydrogen here, so these can be primary or secondary alkyl halides. The first thing that we do is there's an alkylation reaction, a simple SN2 displacement to form the phosphonium. And then we need a base, and if we treat these with bases, they're strong bases typically. Could be butyllithium, could be Grignard, or strong amide bases like KHMDS. It needs you use a strong base so you get an irreversible reaction and you get a displacement or a deprotonation, and that produces the Wittig reagent. So again, a wide variety of substituents can be in these two positions. I'm not even going to list them there. It's almost limitless.